But I'd like to ask right at the beginning, who has been writing Android apps? Probably in the App Store. Well, just a few. And the other ones are seasoned Java developers, I guess. All right. So now let's get right into it. Oops, sorry. You may have heard the news that Android is leaving Harmony behind and is approaching OpenJDK. Now, as a seasoned Java developer, you may be asking, so what? We know what OpenJDK is. And as a seasoned Android developer, you may be scratching your head and maybe saying, what? What does OpenJDK mean? Well, anyway, this talk is about Java on Android. As we've already heard, I usually have to write EJB-based enterprise applications, which is not that interesting. So in my spare time, I decided to do a little bit more fun stuff. I started writing Android apps when the first Android phone, the Google G1, appeared in 2009. 2 years later, I decided to write a book on that topic. And because I think you can only write about things if you've tried them for yourself, I, of course, have written a few apps that you can find on the App Store. If you like, you can join me at Twitter. You, of course, can write me email if you like, and I have a blog where I write mostly about Java and Android. So now let's get right into it. If you are a Java developer coming to Android, you probably ask what Java version does it use? But what does that question imply? Usually if we ask what Java version do we use, we think of Java as some kind of object-oriented programming language. We think of Java about something that runs inside a virtual machine, and we think about Java as something where we have access to a very huge class library. Now the question is, does this apply to Android as well? As a Java developer, we usually see Java as a unity. We usually do not separate between the compiler, the class library, language features. We usually say, well, we have program for Java 6 or we have program for Java 7, and when doing so, we imply that we have several language features at hand. We can make use of lambdas if we use Java 8. And in addition, we have the notion of Java editions, something which has lost most of its interest, Java Mobile Edition, Java Standard Edition for the desktop applications, and Java EE for the enterprise stuff. So again, the question, how does this relate to Android? When we want to know what Java version we are dealing with, we usually consult an old fellow system-get property, which allows us to obtain quite a bit of information about which version the Java class files have, which version the virtual machine has, and things like that. Now, if we run such an application, this was on my Mac with NetBeans and Java 8, we get quite the expected results. But if we run the same application on an Android device, we see something which might be not expected. I've circled it, and at this point we have to say, what? Why do we have Java version 0? If something unexpected happens, it's a good idea to consult the documentation. This is what I've done here. And to our astonishment, Google does say quite a few interesting words. Things are not useful on Android. For example, here, sorry, this doesn't quite work. Google tells us that we cannot use extras, which was a common feature to sideload third-party libraries, which has been deprecated, by the way, but doesn't work on Android at all. And the Java version is not useful on Android as well. So what does that mean? Maybe we just have to rephrase our question, because now we've learned that we cannot answer the question, what Java version does Android use? Maybe we should ask a few other questions instead. For example, what language features can I use? For example, how does the virtual machine behave? Or do I have a virtual machine at all? What classes and packages can I use? Now, essentially, that is what defines the Java programming environment on Android. Some things put straight. We all know that Google never licensed Java from Sun or Oracle. This means that there is no such thing as a JVM on Android. And I guess there probably never will, but we'll come to that later. Instead, there was a clean room implementation which is called Dalvik. Some more of the gossip stuff. Dalvik was once created by a guy named Dan Bornstein, and it was named after an Icelandic fishing village, but that is probably not that important. The more important thing about Dalvik is that it has its own instruction set. It is a genuine virtual machine, but is not compatible with what we call the JVM, and has an alternative layout for its class files. Doesn't call them class files, by the way, and has its own instruction set. The file format is called Dalvik executable, or DEX. And the most important thing about Dalvik is that it was or is optimized for resource-constrained devices. Again, you probably ask yourself, what? If you look inside your pocket and grab those 4 or 8 core smartphone, you probably wouldn't think of something being resource constrained. But that has not always been the case, of course. Let's take a short look in the past. As I said, the first Android device that appeared on market was called the HTC Dream, or in Germany, Austria, and Switzerland, it was called the G1. We could buy it in 2009, and its processor clocked at an astonishing roughly 500 megahertz rate. We had, as you can see, 192 megabytes of RAM. And for us as Java developers, the probably most important thing is that the maximum heap size of that device was limited to 16 megabytes. If you reconsider what we have learned about the new G1 garbage collector, as a quite different kind of beast. So eventually, the maximum heap size of the devices, of course, increased. For example, the Motorola Xoom was the first genuine Android-based tablet that had 48 megabytes of maximum heap size. But nonetheless, the devices were limited regarding capacity, regarding processing speed. And although at that time Sun had an alternative offering, I'm not sure is anyone here still familiar with what was called personal Java. It was a genuine JVM which ran on the same architecture, ARM powered device. There was, let me think, 16 or more years ago, there was a British company called Psion, and they had a very famous range of PDAs or personal organizers, and there was a particular machine called Science Series 5MX, and that device was able to run real Java. It was even able to run Swing at a time when Swing was not part of the core class library, but had to be side-loaded as a separate jar. But the performance was rather weak, and that device had the same issues I have mentioned here. It turned out, however, that Dalvik appeared not to be future-proof. Google admits that though they kept developing Dalvik further, for example with Android version 2.2, which is called Froyo, they even introduced a just-in-time compiler, but Dalvik could not compete with the development speed for the chips for the chipset, and Dalvik as a virtual machine was not very well suited for N-core machines. So they decided to introduce something new. With Android 4.4, there appeared a new runtime environment which was called ART, which reads just Android runtime. And this is a very different approach. Even though Dalvik had its own instruction set, and even though Dalvik had its individual class file format, it was a genuine virtual machine. So if you ran an Android application on a device, essentially there was a thing called virtual machine, which was a Linux binary, and the Android application was running inside that virtual machine. With ART, with a new Android runtime, this dramatically changes as ART features what we call an ahead-of-time compiler. So if you write an Android application at installation time on the device, that application is compiled to a real native Linux executable, which means that the application benefits from all the nifty features modern Linux kernel has. For example, kernel same-page merging, memory compression, and things like that. So Android applications are getting real fast. And that explains why ART is no longer called a virtual machine, but more a runtime environment. Why am I stressing this? Of course, there are several aspects which we get through Java as a programming language that they need to provide. For example, garbage collection. The system behaves as we would expect from Java as a programming language, so we can work with objects just as we would on a regular JVM. And this runtime environment has to be, of course, there, even though the program itself is an ELF binary, which is the native execution unit on a Linux kernel. So now let's take a closer look on how Java moves on the device. So what actually do we have to do if we have a Java program and want to run that on an Android device? First, your program is compiled with the ordinary JavaC compiler. So as one step, we get ordinary class files we are used to as a Java developer. Now this Java class file is taken and converted to what I've already introduced to you, to that Dalvik executable thing. So that is, it is converted to the instruction set for the Dalvik, even though we no longer have Dalvik as a virtual machine on the system. Once that is done, there are quite a few other steps that take place. This all is necessary because once the devices were resource constrained. So there's quite a lot of optimization taking place. In addition, Google offers an obfuscation process which helps protect your program for disassembly or peeking into it. There is a thing called resource shrinking, where duplicate image files are packed together and things like that. Once all that's done, all that stuff is packaged into a so-called APK file, which is the classic installation unit on Android. Fortunately, all this is hidden from the Android developer. This is all done under the hood. You may have heard we used to use Eclipse as the IDE for Android development. Now we have Android Studio, and both toolsets hide that away from us. Still, it may be interesting to peek under the hood, because we've only 40 minutes for the talk. I'm not going to do this live, but I chose to show you what steps you can take if you want to reproduce all that on the command line. As you see, the first step is to compile an ordinary Java source code with Java-C, and then it is further processed with the dx command, and after that this Dalvik executable file is put onto the machine. Well, the funny thing is that you can do this with your device, you can do this with the Android emulator, and you can get a glimpse on what your programming environment does under the hood. At the end of 2014, Google did something interesting. They introduced an experimental new toolchain which they called Jack and Jill. And the main purpose of that new toolchain was to speed up the development process. Remember, I've told you that upon transforming your Java source code to Android executable, there do have to take quite a few steps. And developers complain that transforming those files took too much time, and so Google decided to put a few steps into one tool. And this tool is called Jack. It's called the Java Android Compiler Kit, and Jack is accompanied by something called Jill, which is the Java Intermediate, Java Intermediate Library Linker. So what is the idea behind this? Your Android application will or may use ordinary jars. Maybe you have a third-party library you want to use in your Android application, which you can perfectly do. And Jill will take that jar file and convert it, transform it to the new Jack file format. Java source files are compiled directly to those Jack files as well, and in the end, all those resulting Jack files are melted together and formed an APK and brought onto the device. Something that Google does not promote very prominently is the fact that Jack seems to be derived from the Eclipse compiler plugin. Why am I mentioning this? As we'll see, we get a little bit of trouble regarding language features. More on that soon. So the hope is that when Google uses new versions of the Eclipse compiler plugin, we may get new Java language features sooner than we do get now. More on that in a few minutes. One slide, how it works. Well, as I said, Jill converts reference libraries and packs them into Jack files. They can easily be merged with other Jack files, and in the end, that Jack files are put together and installed on the device. If you are developing Android applications and if you want to try out this new experimental toolchain, you can do so quite easily. You just have to set use Jack as true in your build.gradle file. The only thing you have to be sure of is that the Android build tools are 21.1.1 or greater. This is a nifty side information for you if you want to check if Jack and Jill are active. You can add those two lines in your build.gradle file. This is quite a nifty feature that Gradle has to offer. You can easily access a logger. Logger.quiet means log it anyway. You may be asking yourself why I'm doing something which we are said not to do in Java, that is equal true. I found that the test is more reliable if I do it this way rather than saying not false. This may have to do something with that dynamic languages stuff. Sorry for that. Here we can see that there are reasons why Google calls this new tool chain experimental. I found out that the tool chain has significant problems with spaces in path names or project names, so just be aware of that. Where another important side effect is I measured the turnaround times with the old and the new tool chain, and I think Google has some more homework to do, as the new tool chain, which is supposed to be much faster, takes 3 or 4 times more than the old one. So I'm curious to see when they promote it as the new active tool chain. So now let's stop here for a moment and ask ourselves what happens if Java gets new language features. This has been the case with Java 7, this has been the case with Java 8, and it for sure will be the case for Java 9. So as I've told you, there is a conversation step that needs to take place. We have the Java source file, we have JavaC as Java compiler, or well, the new Eclipse compiler plugin. And the resulting JVM bytecode needs to be transformed. So there is a tool that analyzes the existing class file structure and does something with it. So if we have a language feature that has an impact on the class file layout or the contents of the class files, the tool chain must be aware of that. For example, with the introduction of lambdas in Java 8, the Java compiler utilizes a feature that was introduced with Java 7, which is the invoke dynamic. Invoke dynamic is used to tell Lambda about the object layout, but this is not important here. The important thing is that if I have a Java class file that makes use of a Lambda construct and I have a tool that converts this, then the converting tool must know about at least invoke dynamic, otherwise it won't be able to convert that file. Now the question is, do they? Does the old currently production mode toolchain know about invoke dynamic or Lambda, and will the new Eclipse compiler plugin based toolchain? In Android Studio you have the option to choose what they call the source compatibility version and the target compatibility version. Now currently there is no Java 8 support. So, which of course means that if we are writing an Android application, we cannot make use of lambdas out of the box. Be careful though, because Android Studio has a nifty feature that is called code folding. And if code folding is enabled, if you look at the screen, it appears there might be Lambda code there, but actually it isn't, because what Android Studio just does is compact your anonymous inner class to the new Lambda style syntax, but it is just for viewing purposes. I'm stressing this because if you just have a glimpse at someone's program, you might say, well, they are using lambdas, but in fact they are not. It's just for viewing purposes. If you seriously want or have to use Lambda in your Android application, you can do even now, because there is a really interesting backport of the Lambda features for Java 6 and Java 7. It's called Retro Lambda, and there is an accompanying Gradle plugin which simplifies the process of bringing Java to Android. No, I think I'll skip that online demo. As you see, it's really easy. You just have... No, sorry. I want to show you that. Just a few seconds. That won't work. I wanted to show you how to enable Retro Lambda and the accompanying Gradle plugin, but this doesn't work as expected, so I'm skipping this here. So in a sense, you just have to edit two build.gradle files. Any Android project in Android Studio has two build.gradle files, one that is application specific and one that is a module specific build.gradle file, and you simply have to reference the jar file of the Retro Lambda project, which is on GitHub, and you have to include the Gradle plugin. It's shown on the links at the end of the slide, so if you download them, you can easily check how this is done. Sorry for that. So we now know that we cannot use lambdas in our Android applications, but there are a few interesting language features which we can use already today. One of them is the strings in switch. This new feature has spawned lots of discussions, and I am not going to redo these discussions if a string in switch is an interesting or an annoying language feature. Still, it may be interesting for you to give it a try. Another important new language feature that came with Java 7 is the try with resources feature, which I really like because it puts away quite a lot of boilerplate code. So I advise anybody doing an Android application to make active use of this. Because for us as developers, it's quite interesting no longer to forget closing streams. As you can see on the slide, I have a small demo. You may be wondering why I am overriding the close. I do it just for the sake of logging, because it demonstrates that the close method is actually called. Why am I stressing this? Because this feature, which appears to be a language feature, is relying on something that is not part of the language but of the class library, because we need an implementation of that auto-clausable interface, which is not part of the language but part of the class library. This would have been another demo. I'm not showing this due to the lack of time. But the most important thing, what I want to point out here, is that you can do this on Android, you can use it on Android, but there is a caveat. You can do it starting with API level 19. Short word on the term API level. This is Google's notion of distinguishing Android versions. You probably know that Google is developing Android at a very fast speed. In the beginning, they had 2 or even 3 new Android versions per year. Fortunately, that has slowed down to 1 major release per year, but is still quite fast-paced. And the Android version is measured in terms of the API level. And that auto-clausable interface has been introduced to Android, but it has been introduced with API level 19, which is not that long ago. So what do we learn from this? We see that language features may have influence on the class library, and to use a special feature, we may have several classes or interfaces or other constructs in the class library available. So again, a question is, what class library does Android use? There once was a famous open source project called Apache Harmony, which aimed to be the first open source implementation of Java, and it aimed to unite all open source Java developers under one umbrella. There once was a time that there was no OpenJDK, and so Apache set out to introduce a real open source version of Java with a set of tools, with a set of compiler, with a virtual machine, and of course with a class library. That project was called Harmony, and Harmony had 2 version trains. They had an implementation of Java 5, and they had an implementation of Java 6, each with accompanying compilers, virtual machine, and class libraries. The idea of Apache Harmony was that big companies donate code which make up Harmony. And as we see, this has worked quite well, but as some sort of result or reaction to it, Sun introduced OpenJDK, and in fact that was the end, that was the death of Apache Harmony as a project, because there no longer was the need of an open source implementation or open source version of Java. So what does all that mean? We now know that we have a class library which is based upon Apache Harmony. We have an individual virtual machine that once was called Dalvik and is now called Android Runtime. And we know that Google has been playing with the Apache Harmony class library in adding code that hasn't been there. As you have seen, auto-closable is a feature of Java 7, and as such was never part of the original Harmony distribution. So Google has added quite a bit of code. The problem is that if you see at what's changed in the Java class library since Java 6, not all of these changes have been merged into the old Harmony code. Here are a few examples of things that are not here. These examples are quite random and just show that there is quite a few things that may be interesting to us as Java developers and are missing out of the box. Something that is not there at all is the Java compiler API, which is quite handy if you need to produce bytecode on the fly. The new Java date and time API, which was introduced with Java 8, is not present. Java specification request 223, scripting for the Java platform is not present, and many other things. I've just picked 2 random examples. So the problem is what is present and what is not present cannot be looked up easily. It has to, if you like, be guessed by trial and error. Now the question is, what can we do to add missing features? A lot of features that are now part of the core Java class library emerged as Java specification requests. And a lot of these Java specification requests come with accompanying reference implementations. So the idea is, if there is a reference implementation, why not use that? I have quite a few examples, but time is passing at an enormous speed, so I will have to go over these slides quite quickly. Still, I hope you will get an impression of what can be done and what can't be done. For example, scripting for the Java platform is interesting if you want to access JavaScript or any other scripting language from your Java code. This little program shows how that it's done, and JSR 223 is not present. So you may try to take the reference implementation, which is quite handy as it consists of just 3 jars that need to be deployed. But if you try that, it won't work because the reference implementation is using something which is, well, part of the class library, but is not part of the official API. There is an interesting class called SunMISC-Service, and that class is executed from the reference implementation. So my idea was there is an official version since Java 6, which is called the service loader, which has another differing API, but as you can see here, it is quite easy to make a trivial conversion. So use the new service loader class or implementation and make a version of SunMISC-Service. Now, if you try to use that in combination with the reference implementation of JSR 223, it still doesn't work. At this time, it is because the JavaScript interpreter, which is present of the reference implementation, is called Reno, and it does a funny thing about creating Java classes on the fly. And as you've learned that Android has an alternative representation of class files, it doesn't work out of the box either. I choose to do an alternative version because Android has a JavaScript interpreter on its own, and so I started a small open source project which is called JavaScript Bridge for Android, and it aims to bring those worlds together. At the end of the slides there is a links section, so if you're interested, check out the open source project. It's still in its infancy though. Another interesting thing is taking the Java Date and Time API. There also is a reference implementation, and there is also a backport of the reference implementation, which is called Project 310 backport. And that backport can, in fact, be imported into Android quite easily. You just have to reference the backport in your build.gradle file, as you can see here, and it works out of the box. It is not a real implementation of the new API because, as you see here, the package names differ. But the way the classes work, the way you work with the datetime API is exactly as you would expect taking Java 8 code. So now a quick wrap up. We've seen that Android has quite a bit of difficulties keeping pace with the development of Java as an ecosystem, especially with Java class library and with new language features. The move to OpenJDK may help improve things, as we may gain lots of missing features, a lot of features that are missing right now. We may gain them out of the box. It will be interesting to see how they grow, how they evolve the new Jack and Jill tool chain. The Eclipse compiler plugin is available of Java 8 features, so it will be interesting to see if Java 8 features are brought to Android. Actually, I don't think that we will ever see a real JVM on Android, just because Google has been doing a lot of work in this art runtime environment, and I simply don't think they will give away with that, because what we now have is that an Android application is a real Linux executable, and this is, to me, a killer feature which they would lose if they switched to a classic JVM, so I don't think they will be doing this. Sorry, the last 3 minutes have been rather fast-paced. Still, I hope you liked and you enjoyed the talk, and I wish you guten Appetit then. Thank you.